Okay, here we are for honors physics doing friction, worksheet 5 friction. We're going to go ahead and take a look at problem 7, okay, which is kind of an odd problem, frankly. It says the diagram below shows a large cube of mass 25 kilograms. It's being accelerated across this horizontal level floor by this horizontal force F shoving on it. It says a smaller cube here of mass 4 kilograms is in contact with the front surface. Okay, and they say normally you would expect this block would just fall, but they tell you there's a coefficient of static friction between the cubes that's 0.71. What's the minimum value of this force shoving it so that the small cube will not slide down the side of the large cube, right? So this cube is being pressed into it, so they're being pressed together, right? And while gravity is going to try to slide that little block down, there's going to be enough friction then between those surfaces because this is pressing into it. There'll be friction there that'll keep it from slipping down. How hard do I have to shove on these blocks here, to make there be enough friction that it doesn't slip? That's what we're trying to find. So we want to go ahead and draw our force diagram. Okay, I'm going to go ahead and do that here. Okay. Yeah. Okay. So, I'm going to do two diagrams. I'm going to go ahead and do one for the big cube, and I'll do one for the little cube. Okay, that is my plan. And of course, I'm separating them from each other. I'm doing free body diagrams where they're not touching each other. Okay, let's start with the little cube. I think that'll be easier. Ranged forces, you say there's going to be a gravitational force. You're like, okay, now wait a minute. There's going to be a gravitational force here too. I need to tell these guys apart. I should give the cubes names, okay? I think most people just like to call them A and B. So I'm just going to go ahead and do that today for my examples here. Let's go ahead and call this big block, we'll call him block A, and this little one we'll say is block B. So that means this is the mass of block B times G. Okay, so put a subscript B on that mass. Okay, contact forces now. That's it for ranged forces. Now we go to contact. What's touching this? So the only thing touching the little block is the big block. So then you ask, are those surfaces of the two blocks being pressed together? And you say, yeah, someone is shoving this block A into block B. So there will be a normal force between them. There'll be a normal on B by A. I'm using that double subscript because there's going to be a bunch of normal forces in this problem. So normal on B by A. Once you have a normal force between surfaces, you have to ask, are they going to try to slide past each other? And you say, sure, gravity is going to try to pull, the gravitational force will pull down on B to try to make it slide down on that surface. So if this guy's trying to slide down on that surface, the friction force will oppose the slide. There will be a friction force on B by A. All right, like that. And there's nothing else touching this box, no ropes or wires or anything. So no tensions, so we're done. That's all the forces acting on block B. That's that diagram. Let's go to block A. So we say ranged forces. You say, sure, there's going to be a gravitational force from the center here toward the center of the Earth, mass of A times G. And then you say contact forces, what's touching block A? You're like, well, the floor is touching A, block B is touching A, and then something's exerting this force F. I don't know for sure that's a contact force. I mean, I guess this could be magnetic, be like this is a big magnet and it's a like pole repelling or something, or electrically charged with like charges repelling. I don't know. But I'm going to presume, just go ahead and put that on there. I don't know what that is, but there's some force pushing it here that I'm going to try to solve for. They're calling it big F. So I'm going to use their notation. I'm just going to go ahead and label that big F. All right. And that is, in fact, the force I'm trying to solve for in this problem. All right. Let's see. The other things touching the block we said are the floor and block B. Let's go ahead and do block B next. So the first question is, are those surfaces A and B pressed together? And you say, yeah, we already talked about that. Yeah, they're being pressed together. So there will be a normal force pushing back on this guy. This is the normal force on A by B. And you say, hey, hang on a second. Normal on A by B, normal on B by A. That's a Newton's third law pair. It's one interaction between them pressing on each other. So those are going to be the same. Wick, wick, equal but opposite lengths. Okay, so I can mark them as such. All right. Once I have a normal force on a surface, I can ask, are those surfaces trying to slide past each other? And we already said, yeah. Which way will the friction force go on block A then, up or down? You see, I can think about this a couple ways. One way is I can imagine that if I had, if I had some surface here, and say that I was going to go ahead and press this against the surface and try to slide it down. As this presses against it and slides down, wouldn't it tug down on that surface? Wouldn't that friction tug down on this big surface as this tries to slide down it? So that friction force on this guy is going to be downward along that surface. Friction on A by B. The other thing we can recognize is that, hey, this friction on A by B, friction on B by A, that's a Newton's third law pair. It's one friction interaction between those surfaces. So wonk, 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 those would be equal but oppositely directed. So if this one was up, this one's got to be down. Okay, they're equal and opposite. So there's this friction force along that surface going downward. All right, the last thing touching block A was the floor here. Are they pressed together? Yeah, there's two forces here actually, it turns out, shoving it into the floor. So the floor will push back up with a normal force. This will be the normal force on A by the floor, I guess. I'm going to go ahead and use an F there for floor. Yeah, we'll make that like that. Okay. And then you ask, okay, NAF, right? And then you say, okay, once I have a normal force, I ask, are those surfaces trying to slide past each other? And you're going to say, yeah, this guy's sliding to the right. So there would be friction to the left. But in this problem, they said it's accelerated across a frictionless level floor. So if it's a frictionless level floor, then you say, what they mean to say is that the friction is so small that we can ignore it. We can neglect it. It's negligible friction. So I'm not going to put the friction force on there. And that's it. That's everything touching that block. That's all the forces. We are done. Those are force diagrams. So I ended up with 5 forces on this block and 3 forces on this one. All right, we should choose directions. Okay, this is going to be accelerating along horizontally. So we're going to go ahead and choose to do coordinate axes along the motion and perpendicular to the motion, X and Y. Let's make up and right positive. We're ready to go to sigma F equals ma. So we can try to solve for this force. So we're going to do a calculation with forces. We're going to do sigma F equals ma. Now, how many times can I write sigma F equals ma for this problem? Well, I can do it for the x-axis and the y-axis for block A and the x-axis and y-axis for block B. I can write that equation 4 times. So I'm going to go ahead and write that out. So first, I'm going to write my equations for this guy, and then I'll write my equations for this guy. So for block A, sigma F in the x-axis is mass times acceleration in the x-axis. So forces right minus forces left, that'll be big F minus the normal on A by B, and then equals ma. Well, which m am I talking about here? This equation is just for block A, so this is the mass of A times that acceleration, x-axis. This F is what I'm trying to solve for, but I don't know this normal force. I do know the mass, it's 25 kilograms, but I don't know the acceleration. I actually have 2 unknowns here. 2 unknowns besides the thing I'm trying to solve for. The only thing I know is the mass, actually. So I'm going to have to do some substituting to solve for these guys, so that I can get that friction, that big pushing force. Okay, now I know that this normal force here, you say, hey, that's an action-reaction pair with this normal force here. Let me find that horizontal force equation for this guy so I can get something to substitute in to get rid of that variable. So we're going to go to the equation. I'm going to go ahead and just jump over here and do the equation for this guy. We'll do his horizontal equation. feel like I should probably be labeling somehow that this is for block B and this is for block A, but I kind of think you know. Maybe I'll go ahead and do this. Hey, these are the equations for block A. Here's equations for block B. There we go. All right, here we go. Forces right minus forces left. Hey, there's only one force in that axis there. That's the normal force on B by A, right? And that's going to be equal then to MA. This again is just block B, so this is the mass of B times that acceleration. These two blocks, they are being pressed together, moving together. These accelerations are going to be the same. And this normal on B by A and this normal A by B, they're the same size. So I'm going to be able to do some pretty significant substituting here. Let me go ahead. You can say, for sure, I know that I'm going to want to substitute this MBA. And see, NBA, NAB, same size. I'm going to plug that in there. All right. If I do that, actually, I take it back. I don't want to do that substitution because that'll give me something with an acceleration in the x-axis, but I've already done both my x equations, right? I'm not going to be able to get rid of that A. That's bad news. No. Let's not do that. Let's get rid of the A instead here. Yeah, yep, that's what I want to do. Here's and the reason why, like I said, because if I put that A there and I have A's running around, but I don't have any other equation with horizontal acceleration in it. Okay, so I'm not going to want to actually substitute this in for the normal force and get rid of the normal force because I'll still have that acceleration running around. And you see I've got like three terms. That N is not going to like drop out because I'm not going to divide through by it later. The A is not going to drop out. I'm not going to divide through by A. I'm going to actually add it over. So that wouldn't work. I'd still have the horizontal acceleration that I don't know with no other way of getting it. So actually, I want to get rid of the acceleration. You're like, well, wait, then I'll have that normal force showing up in two terms. How do you get rid of that? Well, it turns out that normal force, shoving them together, that's going to determine how big the friction force is here. So when I substitute in the equation for friction that has mu n, I'll get another n that I can use to get rid of that. So, so I want to get rid of the acceleration here, not the normal force. I don't want to make this substitution. Yep, because I want to get rid of the A. So I'm going to go ahead and I apologize. Let's swap that out. Let's first rearrange this and get that NBA divided by the mass. That's going to be equal to the acceleration. And then that I can substitute over. All right. So I'm not substituting this. Well done. I'm going to substitute from the next line down. I'm going to substitute this in there for A. All right. So yeah, that's the substitution I'm going to want to do. That's exciting. Okay. There we go. So if I make that substitution now, sure, why not? F minus NAB equals mass of A times NBA over mass of B. Okay, there's that substitution there. All right. All right. So now I'm trying to find F. NAB, NBA, they're actually one variable, right? So if I can find the value of that variable, I do know the masses, I can find that force. So I need another equation that's got that normal force. I'm going to find that when I analyze this friction in the vertical axis. So let's look at the vertical axis there. All right. And in this case, you know that we want this block to not accelerate up and down. We want it to stay there on the side, right? Now we want to know what's the minimum force, what's the least hard I have to shove to keep it from slipping. So I'm going to want that friction force to be at its maximum value just barely keeping it from slipping down, so that I'm just pushing just the least I need to keep it from sliding. So that friction force will be at its maximum. So when I do this, we'll do up minus down as MA. You say, I'm going to be looking at it when it's just barely about to slip, but not slipping. So we'll do that friction force on B by A going up minus MBG. And we want that acceleration to be 0. All right? Because we're looking at it when it's just about to slip. Okay, but not sliding down yet, right? Now, if we're just about to slip, that means this is at its maximum static value. Okay, the static friction is at its max value. All right, and our acceleration here is 0. Now, where it's set, so I could move this MBG to the other side if I wanted to, but first let me substitute in, because I'm at the max value, you'll remember that static friction, when it's at its max, that's when it's equal to mu n. All right, just for the maximum static. Okay, and so I can substitute mu n in there. So this will be mu times n. You say, now, we're talking about the normal force friction between B and A, so I want the normal force between B and A. Okay. Okay, so this is it. This NBA is the same as this NBA, which is the same as NAB. So I'm going to go ahead and rearrange. That'll be MBG when I add that over, and then divide by mu. Okay, so this I can put in anywhere where I see this NBA or NAB. So this will go in there and there, right? Okay. All right, so if I do that, this is what this is going to end up looking like. MBG over mu equals mass of A, mass of B, and then where it says normal, we're going to plug in that MBG over mu. All right, you see this mass of B here and here, going to drop out. All right, let me add this term over to the other side. I'm going to have friction, and I see how this term and this term have the same denominator, so I can actually just add it on the numerators. So it's going to be mass of A times G, and then I'm going to add another mass of B times G. All right, over mu. So that looks like that is it. I do know values for all this stuff, so I can solve for F. All right, and let's see here. This is 25 kilograms. G is 9.8, plus the little block had a mass of 4 kilograms, times G is 9.8. And the mu, the coefficient of friction between the surfaces, was 0.71. And so if I do this, let's see what we get. I do 25 times 9.8 plus 4 times 9.8, divide that total by 0.71, and I get 400.28 newtons. I'm just going to round off to 400.3 newtons. I suppose I don't have enough sig figs. I probably ought to just round it to 400, but that's okay. 400.3 newtons is my answer. That's how hard I have to shove on it so that it stays in contact and that block does not slip down the surface. Okay, and that is problem 7.